Hello and welcome once again to the Clements Corner. Here is your dashing and brilliant host, Mr. Clements.
Who's a cutie doo-doo poo? A stoopy poopy,
Oh, hey, hi students, didn't see you there. Well, on today's episode, we'll be recapping the physics of motion. Sir Isaac Newton was one of the founding fathers of physics. Newton came up with three basic laws that govern all types of movement. Newton's first law states that an object stays at rest or in motion unless acted on by an unbalanced force. This is also known as the law of inertia. Today, we'll look at what this means and how it applies to our lives. Why, I remember that time when I had a good old-fashioned... This has been the Clements Corner with Mr. Clements. Now enjoy the rest of your learning experience. Tune in next time to hear Mr. Clements talk about why hearing Yanny makes you big-brained. I hope you enjoyed that super-duper fantastic animation at the beginning and showing the whole series that I'm doing today. This is going to be completely about inertia. I'm going to give you three cool examples of real-life inertia in use. The first one I'm going to kind of prelude to with this quick cool video that I just compiled. These are all a bunch of people doing something called a stoppie. It's where you use your inertia to propel yourself forward without going completely over the end of a bicycle or a motorcycle or an ATV or whatever. So I'm gonna show a little bit more about it here in just a second, but for now, just enjoy the rest of this. Hey teacher.
Yes, my student?
What does this have to do with anything?
Well, we're talking about bikes, and the movement of bikes is all about inertia.
Oh, cool. Thanks.
You're welcome.
A lot of y'all probably don't know this, but I have been getting into mountain biking, and I thought I should give this a try. So here it is. Well, it took some practice, but I got it. Important thing here is take a look at, you can see exactly when the bike stops, but my inertia keeps going. Let me explain that in a little bit more detail. So here's the bike tire. You can see the handlebars facing about this direction, and my mass is on this side. All of the mass is going in this direction. But whenever I squeeze the brakes, you can see here's the wheel. The handlebars are now changing direction. The wheel is not moving, but the inertia does not like to stop. It doesn't like to change its movement. So all the mass is still trying to go in the same direction. And so it kind of does. And this is at the very top of when I finally decided to let go of the brakes. You can see that the handlebars are much more steep of an angle. The wheel is still not moving at all. And my mass has inertia. The inertia's still going. If I wouldn't have let go, then I would have continued going forward and flipped over the handlebars. Alright, so hopefully you guys enjoyed that last video. I know I had lots of fun making it. This next demonstration is going to be with water balloons. There are plenty of other videos out there that are kind of like this, but this video is going to be describing it specifically in terms of inertia. So here it comes. I hope you enjoy. So it's important to remember that inertia means something with mass does not want to change its motion. So whenever I slap the balloon, I'm creating an unbalanced force. And where the water has not yet moved, its inertia is what's keeping it in place. So after the shock wave of my force moves through the entire balloon, then the water or the balloon itself starts to move. Good? So here's the other example. When I'm slapping the balloon, I'm creating an unbalanced force, but the force has not touched this side of the balloon. So you can see the wave is moving across, the unbalanced force is moving, but this side over here, its inertia is still keeping it in place. Until finally, the shock wave of the unbalanced force gets to it and causes it to move. What does he even mean by that?
Great question. Water is made up of water molecules. Each water molecule has its own inertia. So you have to hit each water molecule in time to get the inertia to go from one side of the water to the other side of the water.
How did you get in my house?
Physics.
Yeah, I guess that makes sense. So that one was an example of a balloon not moving with a force acting on it. This one is the balloon is moving. Its inertia is trying to stay in motion. So when it hits the ground, that's the unbalanced force, even though the top, its inertia is keeping it in place. So the further down that it continues to move, the more the ground is coming up and pushing on it, even though the top is still not moving, until finally the whole entire thing is hitting the ground. Okay, so that's 2 demonstrations down. We're on to our last one. So this last one, we're going to be seeing how mass can affect our inertia. To do this, we're going to head to the grocery store. I know it's Corona season, but we'll be careful. See you soon.
Oh, man.
So as you can tell from the lack of video, Walmart did not like me videoing inside the store for whatever reason. So I'll just kind of tell you about what was going on. So I went inside, got a cart, and then put some stuff in the cart to change the mass. Cart A had water bottles in it. Cart B was empty. So on your papers, you've got a question that says which one has more inertia, Cart A or Cart B? Choose now.
It's B, duh.
If you picked B, you're no longer allowed to be in my class anymore.
You can just leave. Go. Get out of here. Ah!
And back to the demo. Alright, so the audio was horrible in Walmart. They didn't want me to record there anyway, so I'm just going to voice over what I was saying. This thing is a force sensor, and it measures how much force I'm pushing with. So I'm just going to push it on the cart, and it'll tell me how much force I'm pushing over time. Here's the graph for that, which you are going to be drawing in your papers. Go ahead and pause the video, do that now. And now we're going to add weights. Yeah, sorry if my butt got in your face there. Anyway, back to this. So I'm pushing it again, this time with the weights inside. Here's the data for that one. Make sure that you copy it down. So this one is showing both pieces of data. The green one is showing how much force it took with the water bottles inside. The blue one is how much force it took without the water bottles. So you can see that the green one is about 20 newtons of force. That's with the bottles, and then the one without the bottles was about 12 newtons of force. So if it takes more force to change the motion, that means that it has more inertia. And that's what we learned. Alright, that's it. Thanks for watching, guys. Hope you learned something. A special shout out to my animator Runty Art. You can check out some of her stuff here. And I'll see y'all later.